Welcome to Sleepy Science Hub. As you settle in tonight, let me know where in the world and at what time you're watching. Perhaps you're lying beneath a starlit sky, or maybe you're in a cozy room with the gentle darkness of evening surrounding you. Wherever you find yourself, whatever hour has brought you here, you've arrived to explore one of the most beautiful and profound mysteries of existence. The gentle rhythm that governs everything we know, a cosmic breathing pattern so vast and slow that it encompasses all of space and time itself. Tonight, we'll discover what happens when a universe takes a breath, how this cosmic respiration shapes reality, and how we ourselves are part of this infinite, peaceful rhythm. Now, get comfortable. Let your own breathing slow and deepen. Take a gentle breath along with the cosmos itself, and let's begin. In the quiet moments when you focus on your own breathing, feeling the gentle rise and fall of your chest, the slow rhythm of air flowing in and out of your lungs, you're participating in one of the most fundamental patterns that governs all existence. But what you might not realize is that this same essential rhythm, this pattern of expansion and contraction, of breathing out and breathing in, operates on scales so vast and timescales so immense that they encompass the entire universe itself. Just as your body breathes in cycles that sustain your life, the cosmos breathes in cycles that sustain all of reality. To understand this cosmic breathing, imagine that you could somehow step outside of space and time, positioning yourself in a place where you could observe the entire universe as a single living entity. From this impossible vantage point, you would see something that would fundamentally change how you think about existence itself. The universe, in all its incomprehensible vastness, would appear to be breathing, not with the quick, biological rhythm of earthly life, but with a breath so slow and deep that each cycle takes billions upon billions of years to complete. Right now, at this very moment, as you listen to these words, the universe is in the middle of a vast exhale that began nearly 14 billion years ago. This cosmic breath is so gentle and gradual that from our human perspective, it appears as a steady, unchanging expansion, the slow stretching of space itself that carries galaxies away from each other like leaves floating on the surface of a pond that is slowly, peacefully growing larger. When astronomers first discovered this expansion in the early 20th century, they found that every galaxy they could observe was moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This wasn't because these distant stellar islands were flying through space away from our location, but because space itself was expanding, carrying everything along with it in the most gentle and universal motion imaginable. Picture, if you will, a balloon being inflated very slowly and steadily. If you were to draw dots on the surface of the balloon to represent galaxies, you would notice that as the balloon expands, every dot moves away from every other dot, with the distances between them growing larger over time. No single dot is the center of the expansion. From the perspective of any dot, all the other dots appear to be moving away from it. This is remarkably similar to what happens in our expanding universe, except that instead of a two-dimensional balloon surface, we're dealing with a three-dimensional fabric of space itself. The rate of this cosmic expansion is determined by what scientists call the Hubble constant, named after Edwin Hubble, who first measured this universal recession of galaxies. Currently, this expansion means that for every million parsecs of distance, about 3.26 million light-years, space is expanding at a rate of approximately 70 kilometers per second. This might sound fast, but when you consider the vast scales involved, it represents an incredibly gentle, gradual process. To put this expansion rate in perspective, imagine two galaxies that are currently separated by a distance that light takes 100 million years to cross. Due to the expansion of space, after another 100 million years pass, these galaxies will be separated by a distance that light takes about 107 million years to cross. The change is real and measurable, but it occurs so gradually that from any local perspective, it will be imperceptible across human timescales. This expansion affects everything in the universe, but its effects are most noticeable on the largest scales. Within our own galaxy, the Milky Way, the gravitational forces that hold stars and solar systems together are far stronger than the gentle pull of cosmic expansion. So locally, things remain stable and bound together. It's only when you look at the spaces between galaxies and galaxy clusters that the expansion becomes apparent and significant. As space expands, it carries with it not just matter, but also energy and even light itself. The light from distant galaxies gets stretched along with the expanding space it travels through, causing what astronomers call redshift. Light that was emitted as blue or ultraviolet from a distant star might reach us shifted toward the red end of the spectrum, or even in infrared wavelengths we can't see with our eyes. This redshift serves as a kind of cosmic speedometer, telling us how fast space was expanding when that light began its journey to us. The expansion also affects the cosmic microwave background radiation, the afterglow of the Big Bang that fills all of space. This ancient light has been stretched by the expansion of space from what were originally high-energy gamma rays down to gentle microwave radiation that we can detect with sensitive instruments. This radiation provides us with a baby picture of the universe, showing us what conditions were like when the cosmos was only about 380,000 years old and space was much smaller and denser than it is today. One of the most beautiful aspects of cosmic expansion is its uniformity and smoothness. Unlike earthly processes that might be chaotic or irregular, the expansion of space proceeds with remarkable consistency and gentleness. There are no sudden accelerations or decelerations, no violent changes in direction, just the steady, peaceful breathing out of space itself, creating room for new possibilities and new forms of beauty to emerge. This expansion has been the creative force behind much of the beauty and complexity we see in the universe today. In the very early universe, when space was much smaller and everything was much closer together, conditions were too hot and dense for atoms to form, let alone stars, planets, or life. It was only as space expanded and cooled that the first atoms could come together, that gravity could begin to collect matter into the first stars, and that the long process of cosmic evolution could begin. The expansion continues to shape the universe today, influencing the formation of new stars, the evolution of galaxies, and even the ultimate fate of all the matter and energy in existence. As space continues to expand, the average density of matter decreases, which affects how gravity can pull things together to form new structures. In regions where matter is slightly denser than average, gravity can overcome the expansion and create bound systems like galaxies and galaxy clusters. In regions where matter is less dense, the expansion wins out, creating vast cosmic voids where very little matter exists. The rhythm of expansion also affects the very fabric of space-time itself. According to Einstein's theory of general relativity, mass and energy curve space-time, creating what we experience as gravity. As the universe expands and the distribution of matter changes, these curvatures in space-time evolve as well, creating a dynamic, ever-changing geometry for the cosmos. Perhaps most remarkably, recent observations have revealed that the expansion of the universe is actually accelerating. Something that scientists call dark energy appears to be causing space to expand faster and faster over time, like a cosmic breath that is gradually speeding up. This dark energy makes up about 68% of all the energy in the universe. Yet we understand very little about what it actually is or why it has this effect. This acceleration means that the cosmic breathing pattern is more complex than a simple in and out rhythm. Instead of eventually slowing down and perhaps reversing into a cosmic inhale, the current expansion appears to be entering a phase where we'll continue indefinitely, with galaxies being carried ever farther apart until they disappear beyond each other's cosmic horizons. Yet even in this scenario of eternal expansion, there remains something profoundly peaceful and beautiful about the process. The universe continues its gentle breathing out, creating ever more space for existence, ever more room for the cosmic story to unfold. In this vast exhale, we find ourselves not as passive observers, but as active participants, made of matter that was forged in the hearts of ancient stars, breathing air that connects us to every other living thing on Earth, thinking thoughts that represent the universe becoming conscious of itself. As you rest now in the awareness of this cosmic expansion, feeling perhaps your own breath synchronizing with these vast rhythms, consider how every atom in your body has been part of this cosmic breathing for billions of years. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it has been carried along by the expansion of space. Part of the universe's gentle exhale that continues even now, creating the conditions that allow for your existence and your capacity to contemplate these profound mysteries. The gentle rhythm of expansion that surrounds us and includes us continues with the same patient persistence it has shown for nearly 14 billion years, carrying us all forward into an ever-expanding future filled with infinite possibilities for beauty, discovery, and wonder. As you settle deeper into contemplation of the cosmic breath, feeling perhaps the way your own breathing naturally synchronizes with the rhythm of these vast thoughts, you begin to sense something profound about the nature of the universe's current phase. What we are experiencing right now, in this moment, and in every moment of cosmic history since the Big Bang, is the universe in the midst of a great exhale, a cosmic breathing out that has been gently and steadily continuing for nearly 14 billion years, creating space, time, matter, and all the conditions necessary for existence itself. To truly appreciate the magnitude and beauty of this great exhale, imagine that you could somehow experience time on cosmic scales, where billions of years pass like minutes, where the formation and death of entire galaxies unfolds like the blooming and fading of flowers in a vast cosmic garden. From this perspective, you would witness the universe's breath as a single, continuous, peaceful exhalation that began with what we call the Big Bang and continues to this very moment, carrying with it all of space, all of time, and all of existence. This cosmic exhale began not as an explosion in space, but as an expansion of space itself. In those first incomprehensibly brief moments after the beginning, space expanded from a size smaller than a subatomic particle to something approaching the size of a grapefruit. And this expansion happened so rapidly that it defied every intuition we have about the nature of time and space. Yet even this period of cosmic inflation, as scientists call it, was not violent or chaotic, but rather represented the universe finding its rhythm, establishing the fundamental pattern of expansion that would characterize its breathing for billions of years to come. As the initial cosmic inflation slowed and settled into the more measured pace of expansion we observe today, the universe entered what we might think of as the main phase of its great exhale. Space continued to grow larger, but now at a rate that allowed for the gradual cooling and organization of matter that would eventually lead to the formation of the first atoms, the first stars, and ultimately all the complex structures we see in the cosmos today. During this great exhale, space itself acts as the medium through which the cosmic breath flows. Unlike the air that moves in and out of your lungs, which travels through existing space, the cosmic breath is the movement of space itself. As the universe exhales, it doesn't push matter through space. Instead, it carries matter along as space expands, like a gentle current that bears everything along with it without resistance or friction. The rate of this cosmic exhalation varies across different epochs of universal history, creating a kind of cosmic breathing pattern with its own natural rhythms and phases. In the very early universe, the expansion was extremely rapid, with space growing larger at rates that would seem impossible if applied to any material object. As time passed and the universe aged, this expansion rate gradually slowed, like a breath that begins as a quick gasp and then settles into a steady, measured rhythm. But then, remarkably, about 5 billion years ago, something changed in the cosmic breathing pattern. Instead of continuing to slow down as it had been doing for nearly 9 billion years, the expansion began to accelerate again. This acceleration represents a new phase in the universe's great exhale, as if the cosmic breath had found a second wind and begun to breathe out even more vigorously than before. This acceleration is driven by what cosmologists call dark energy, a mysterious component of the universe that makes up approximately 68% of all the energy and matter in existence. Dark energy acts like a kind of cosmic anti-gravity, not pulling things together as ordinary gravity does, but instead pushing space itself to expand faster and faster. In a metaphor of cosmic breathing, dark energy acts like the force that drives the great exhale, ensuring that the universe continues to breathe out with increasing vigor rather than slowing down or reversing direction. The effects of this accelerating expansion ripple through every aspect of cosmic structure and evolution. Galaxies that were once slowly moving away from each other are now being carried apart at ever-increasing rates. Galaxy clusters that might have continued to grow larger through gravitational attraction are instead being prevented from incorporating new members as the expansion carries potential new galaxies too far away to be captured. Yet despite this acceleration, the great exhale remains fundamentally gentle and gradual from any local perspective. The expansion doesn't tear apart bound systems like galaxies, solar systems, or even atoms. Instead, it works only on the largest scales, affecting primarily the distances between galaxy clusters and the overall geometry of space itself. Within our own galaxy, within our solar system, even within the space between Earth and the Moon, the effects of cosmic expansion are utterly negligible compared to the gravitational and electromagnetic forces that hold these systems together. This selective nature of cosmic expansion creates a beautiful hierarchy of stability within the breathing universe. On the smallest scales, the fundamental forces of nature keep atoms and molecules intact, allowing for the complex chemistry that makes life possible. On intermediate scales, gravity maintains the integrity of planets, stars, and galaxies, creating stable environments where evolution and development can occur over billions of years. Only on the very largest scales does the cosmic breath assert itself, gently carrying the largest structures of the universe apart, while leaving the smaller, local patterns of organization undisturbed. As you contemplate this great exhale, you might wonder about its ultimate destination and purpose. Where is all this expanded space going? What is the universe breathing into? These questions touch on some of the deepest mysteries of cosmology and remind us that our understanding of the cosmic breath is still evolving and incomplete. One way to think about the destination of the cosmic exhale is to recognize that space itself is not expanding into anything else. There is no external container or void that the universe is growing to fill. Instead, space is creating itself as it expands, bringing new regions of existence into being with each moment of the cosmic breath. The universe is not breathing into pre-existing emptiness, but rather breathing existence itself into being, creating the very concepts of here and there, near and far, as it exhales. This creative aspect of the cosmic breath means that the great exhale is not just moving things around, but actually generating new possibilities for existence. Every cubic meter of space that comes into being through expansion represents new potential for matter and energy to interact, new regions where stars might form, new territories where life might eventually emerge. The cosmic breath is thus not just a redistribution of what already exists, but an ongoing act of creation that continues to expand the realm of the possible. The timeline of this great exhale stretches from the very beginning of time into a future so distant that it challenges human comprehension. If current models of cosmic evolution are correct, the universe will continue this phase of accelerating expansion for trillions upon trillions of years, carrying galaxies so far apart that future observers in any given galaxy will see a universe that appears to contain only their own galaxy, with all others having been carried beyond the cosmic horizon where their light can no longer reach across the expanded space. Yet even this seemingly endless exhale may not represent the final chapter in the universe's breathing pattern. Some theoretical models suggest that dark energy itself might evolve over time, potentially changing its effect on cosmic expansion. Other models propose that the universe might eventually transition from expansion to contraction, beginning a cosmic inhale that would reverse the great exhale and bring everything back together again in what cosmologists call the Big Crunch. These possibilities remind us that the cosmic breath we are currently experiencing represents just one phase in what might be an eternal cycle of cosmic breathing, with each complete breath spanning timescales so vast that the current age of the universe might represent merely the first few moments of the cosmic exhale. From this perspective, we find ourselves living not at the end of cosmic history, but at the very beginning, witnessing the universe as it takes its first tentative breaths in what might be an infinite sequence of cosmic respiration. The beauty of existing within this great exhale lies partly in its combination of overwhelming scale and intimate connection. While the cosmic breath operates on scales that dwarf human comprehension, it also includes and encompasses every aspect of our existence. The space between the letters on this page, the air in your lungs, the distances between atoms in your body, all of it participates in the cosmic expansion. All of it is carried along by the universe's great exhale. This participation means that you are not separate from the cosmic breath, but an integral part of it. Every breath you take involves air molecules that have been carried by cosmic expansion across billions of years of space and time. Every thought you think occurs within a brain made of matter that has participated in the cosmic exhale since the very beginning of time. In a very real sense, your consciousness represents the universe becoming aware of its own breathing, experiencing its own expansion from within. As you rest now in this awareness, feeling perhaps the way your own gentle breathing mirrors and participates in the cosmic pattern, you can sense yourself as both an observer and a participant in the universe's great exhale. You are breathing along with the cosmos, carried forward by the same gentle force that has been expanding space and creating possibilities for nearly 14 billion years. In this recognition, the vast scales of cosmic breathing become not intimidating but comforting, reminding you that you are held within a process so fundamental and enduring that it encompasses all of existence, while remaining as natural and peaceful as your own breath flowing in and out of your lungs. As the cosmic breath continues its gentle exhale, something beautiful and profound is happening in the spaces between things, in the growing distances between stars, between galaxies, between the largest structures in the universe. These expanding spaces are not empty voids waiting to be filled, but rather dynamic regions where some of the most subtle and important processes in cosmic evolution unfold. To truly understand what happens when the universe takes a breath, we must turn our attention to these in-between places, these cosmic intervals that grow larger with each moment of the great exhale. Imagine, if you will, that you could take a journey through one of these expanding cosmic spaces, perhaps traveling through the gulf between our Milky Way galaxy and our nearest large galactic neighbor, Andromeda. This journey would take you through a region that, while appearing empty to casual observation, is actually filled with wonders that reveal themselves only to patient and careful attention. As you drift through this intergalactic space, carried along by the gentle current of cosmic expansion, you would discover that the universe's breathing creates not emptiness, but opportunity, not void, but potential. The space between galaxies contains what astronomers call the intergalactic medium, an extremely thin soup of gas, dust, and other matter that fills the apparent emptiness with subtle substance. This medium is so diffuse that it contains only about 1 atom per cubic meter, making it far more tenuous than the best vacuum we can create in laboratories on Earth. Yet despite its incredible thinness, this intergalactic medium plays crucial roles in cosmic evolution, serving as a reservoir of raw materials for future star formation and as a medium through which galaxies can interact and exchange matter across vast distances. As cosmic expansion carries galaxies farther apart, The intergalactic medium stretches and thins along with the expanding space it occupies. Gas that was once dense enough to participate in active star formation becomes too diffuse to collapse under its own gravity, effectively removing it from the star-forming process. This cosmic dilution represents one of the ways that the universe's breath influences the evolution of galaxies and stars, gradually reducing the raw materials available for new stellar births as the Great Exhale continues. The expansion also affects the temperature of this intergalactic medium in fascinating ways. As space expands, any gas contained within it undergoes what physicists call adiabatic cooling, the same process that makes the air inside a tire cool when you let the pressure out. This cosmic cooling has been occurring throughout the universe's history, gradually reducing the temperature of intergalactic gas from the incredibly hot conditions that existed in the early universe to the frigid state we observe today. In the vast spaces between galaxies, you would also encounter something even more mysterious and fundamental than ordinary matter. The dark matter that makes up approximately 27% of the universe's total mass and energy. This dark matter, which interacts only through gravity and remains invisible to direct observation, forms a kind of cosmic scaffolding that gives structure to the expanding universe. As space expands, this dark matter scaffolding stretches as well, but its gravitational influence continues to guide the formation of cosmic structures across billions of years. The cosmic web formed by dark matter creates a network of filaments and nodes that spans the entire observable universe, with galaxy clusters forming at the intersection points where multiple filaments meet. As the universe continues to exhale, this cosmic web evolves and changes, with some connections being stretched to the breaking point, while new patterns of organization emerge in response to the ongoing expansion. Perhaps most remarkably, the expanding spaces between galaxies contain regions where virtual particles spontaneously appear and disappear in accordance with the principles of quantum mechanics. These quantum fluctuations occur constantly throughout empty space, creating a subtle energy known as vacuum energy or zero-point energy. As space expands, new regions of vacuum come into existence, each filled with their own quantum fluctuations, adding to the total energy content of the universe in ways that may contribute to the mysterious dark energy that drives cosmic acceleration. The radiation that travels through these expanding spaces tells its own story of cosmic breathing. Light from distant galaxies, traveling for billions of years through expanding space, arrives at our telescopes carrying information about the universe's history encoded in its wavelength and intensity. This light has been stretched by the expansion, with photons that began their journey as high-energy ultraviolet or even X-ray radiation arriving as gentle visible light or infrared energy. This stretching of light creates one of the most beautiful effects of cosmic expansion, the way that distant galaxies appear to glow with a warm, reddish light that speaks of the vast distances their light has traveled and the billions of years of cosmic breathing that have occurred during that journey. The farther away a galaxy is, the more its light has been stretched by expansion, creating a natural hierarchy of colors that allows astronomers to gauge cosmic distances simply by observing the hues of distant stellar systems. As you contemplate these expanding cosmic spaces, you begin to understand that the universe's breath creates not just physical distance, but temporal distance as well. When we look out into space, we're also looking back in time, seeing galaxies as they were when their light began its journey toward us. The most distant galaxies we can observe appear to us as they were when the universe was only a few 100 million years old, showing us cosmic nurseries where the first generations of stars were just beginning to form. This temporal dimension of cosmic expansion means that the spaces between galaxies serve as a kind of cosmic museum, preserving images of the universe at different ages for us to study and contemplate. The cosmic breath has carried these ancient images to us across billions of years, allowing us to witness the universe's youth and observe how cosmic structures have evolved as space has expanded. The expansion also affects the fundamental physics operating in these cosmic spaces. As space grows larger and matter becomes more dilute, the average density of the universe decreases, which in turn affects how gravitational fields evolve and how new structures can form. In the early universe, when everything was much closer together, gravity was more effective at pulling matter into dense concentrations that could form stars and galaxies. As expansion continues and the average density drops, it becomes increasingly difficult for gravity to overcome the cosmic breathing and create new bound structures. This gradual shift in the balance between expansion and gravitational collapse has profound implications for the future evolution of cosmic structure. While gravity can still form new stars within existing galaxies where matter remains sufficiently concentrated, the formation of entirely new galaxies becomes increasingly rare as the cosmic exhale carries potential building materials too far apart for gravity to collect them effectively. The spaces between galaxies also serve as highways for cosmic rays, high-energy particles that travel across intergalactic distances, carrying information about violent events in distant corners of the universe. As space expands, these cosmic rays also lose energy through the same process that redshifts light, arriving at Earth with energies that reflect both their original acceleration and the cosmic expansion that has occurred during their journey. Magnetic fields thread through these expanding spaces as well, creating invisible networks that can influence the motion of charged particles across cosmic distances. These intergalactic magnetic fields are incredibly weak compared to the magnetic fields we experience on Earth, yet they play important roles in cosmic evolution by affecting how matter and energy flow between galaxies and how cosmic rays propagate through the universe. Perhaps most mysteriously, the expanding spaces between galaxies may contain clues to some of the deepest questions in cosmology and physics. The dark energy that drives cosmic acceleration appears to be uniformly distributed throughout space, meaning that as new space comes into existence through expansion, it brings with it new sources of dark energy. This suggests that the vacuum of space itself may possess intrinsic properties that we do not yet understand, properties that become apparent only when we consider the behavior of space on cosmic scales. Some theoretical physicists propose that these expanding cosmic spaces might contain extra dimensions beyond the three spatial dimensions we can directly observe. These additional dimensions, if they exist, would be curled up so tightly that they remain invisible at ordinary scales. But their effects might become apparent in the way that space expands and in the fundamental forces that operate across cosmic distances. The temperature of these intergalactic spaces tells its own story of cosmic breathing. The cosmic microwave background radiation that fills all of space has been cooling steadily as the universe expands, dropping from thousands of degrees in the early universe to just a few degrees above absolute zero today. This radiation represents the afterglow of the Big Bang, stretched and cooled by billions of years of cosmic expansion until it now appears as a gentle microwave hiss that permeates every cubic centimeter of space. As you drift through these expanding cosmic spaces in your imagination, you begin to appreciate how the universe's breath creates not emptiness but richness, not simplicity but complexity. Every cubic meter of apparently empty space between galaxies contains quantum fluctuations, dark matter, cosmic rays, magnetic fields, and ancient light, all of it participating in the cosmic expansion while maintaining the delicate conditions necessary for continued cosmic evolution. The gentle stretching of these spaces represents one of the most profound aspects of cosmic breathing. The way that expansion creates new possibilities for existence, while preserving the essential patterns and relationships that allow complexity and beauty to emerge. As galaxies move farther apart, new regions of space come into being, each filled with its own potential for future developments in the cosmic story. In these growing spaces between the stars, between the galaxies, between the largest structures in the cosmos, we find not the absence of significance, but rather the subtle presence of processes that operate on scales and timescales that dwarf human experience, yet remain as gentle and natural as the breath that flows in and out of your lungs as you rest in contemplation of these cosmic mysteries. As the universe continues its great cosmic exhale, breathing space into existence, and carrying matter gently apart across ever-increasing distances. Something profoundly beautiful and fundamental is happening to all the energy that fills the cosmos. Like a gentle whisper that grows softer as it travels farther from its source. The energy of the universe is slowly, peacefully cooling as space expands, creating a cosmic temperature drop so gradual and universal that it affects every particle, every wave of light, every quantum fluctuation throughout all of existence. To understand this cosmic cooling, imagine that you could somehow sense the temperature of space itself as you float weightlessly through the expanding universe. You would discover that this cooling is not like the familiar drop in temperature you might experience on a winter evening, where cold air replaces warm air in your immediate environment. Instead, this is a cooling that happens to the very fabric of space and time, a reduction in the fundamental energy density of the universe that occurs everywhere simultaneously as the cosmic breath gently stretches reality itself. This universal cooling began in the earliest moments after the Big Bang, when the universe was unimaginably hot and dense, filled with energy so intense that matter, as we know, it could not exist. In those first fractions of a second, the temperature of the universe measured in the trillions of degrees, hot enough to break apart any atomic nuclei, hot enough to convert matter and energy freely back and forth, according to Einstein's famous equation, E equals mc squared. As space began to expand in those first moments of cosmic breathing, this enormous energy began to spread out over ever larger volumes, initiating the cooling process that continues to this day. The mechanism of this cosmic cooling is elegantly simple, yet profound in its implications. As space expands, any energy contained within it becomes diluted, spread over a larger volume, just as a drop of ink becomes fainter when mixed into an ever larger pool of water. But unlike the ink analogy, where the total amount of ink remains constant, the expansion of space actually affects the fundamental nature of energy itself, stretching wavelengths and reducing frequencies in a process that transforms the character of light and heat throughout the cosmos. Photons, the particles of light and electromagnetic radiation, provide perhaps the most beautiful example of this cosmic cooling process. When a photon is traveling through expanding space, the expansion literally stretches the wavelength of the light, shifting it toward the red end of the electromagnetic spectrum. A photon that began its journey as high-energy gamma radiation might arrive at its destination as visible light, or even as gentle infrared radiation, having been cooled by billions of years of cosmic expansion. This stretching of light reveals itself in the cosmic microwave background radiation, which fills every cubic centimeter of space throughout the universe. This radiation represents the afterglow of the Big Bang, light that was emitted when the universe was only about 380,000 years old and had cooled enough for the first atoms to form. At that time, this radiation had the intensity and temperature of the surface of a star, glowing with bright visible light that illuminated the young cosmos. But as space has expanded over the past 13.8 billion years, this primordial light has been stretched and cooled until it now appears as gentle microwave radiation with a temperature of just 2.7 degrees above absolute zero. This cosmic background radiation serves as a kind of universal thermometer, telling us the current temperature of space itself and providing direct evidence of the cosmic cooling that has been occurring throughout the universe's history. The cooling whisper of cosmic expansion affects not just light, but all forms of energy in the universe. The kinetic energy of particles moving through space decreases as expansion changes the reference frame in which their motion is measured. The potential energy stored in gravitational fields changes as matter spreads out over larger distances. Even the quantum vacuum energy that fills empty space responds to the expansion, creating subtle effects that may contribute to the mysterious dark energy that drives cosmic acceleration. As temperatures drop throughout the expanding universe, different physical processes become possible or impossible, creating a kind of cosmic timeline marked by temperature milestones. In the extremely hot early universe, fundamental forces that we now observe as distinct, the electromagnetic force, the weak nuclear force, and possibly even gravity itself, were unified into a single, more fundamental interaction. As cosmic cooling progressed, these forces separated from each other in a series of phase transitions, each one occurring when a universal temperature dropped below a critical threshold. The cooling also enabled the formation of increasingly complex structures as the universe aged. When temperatures were too high, atomic nuclei could not hold onto electrons to form stable atoms. As cooling progressed, the first hydrogen and helium atoms could form, making the universe transparent to light for the first time. Further cooling allowed gravity to collect matter into the first stars, where nuclear fusion could begin, creating heavier elements and warming local regions of space even as the universe as a whole continued to cool. This interplay between cosmic cooling and local heating creates one of the most beautiful aspects of universal evolution. While the overall trend is toward lower and lower temperatures as space expands, pockets of concentrated matter can heat up dramatically through gravitational collapse and nuclear fusion. Stars represent islands of intense heat in the cooling cosmic ocean, their nuclear furnaces creating the heavy elements necessary for planets and life, while their light warms local environments against the general cooling trend. The rate of cosmic cooling has changed throughout the universe's history, reflecting the changing dynamics of expansion itself. In the early universe, when radiation dominated the energy density, cooling occurred more rapidly than it does today. As matter began to dominate over radiation, the cooling rate decreased. Now, as dark energy drives accelerating expansion, the cooling rate is changing again, though so gradually that the effects will become apparent only over cosmic timescales. The cosmic cooling also affects the evolution of galaxies and galaxy clusters in subtle but important ways. As the universe cools, the intergalactic medium becomes less energetic, making it easier for gravity to pull gas into galaxies where it can form new stars. However, this same cooling also makes it more difficult for galaxies to heat and expel gas that might otherwise be recycled into future star formation. These competing effects help determine the rate at which stars form throughout cosmic history. The temperature of dark matter, that mysterious component that makes up most of the universe's mass, also responds to cosmic expansion, though in ways that are still not fully understood. Dark matter particles, whatever they may be, were presumably in thermal equilibrium with ordinary matter in the early universe, sharing the same high temperatures. As expansion and cooling proceeded, dark matter may have frozen out of thermal equilibrium, maintaining its own temperature evolution that follows different rules from ordinary matter. The cooling whisper of cosmic expansion even affects the fundamental constants of nature in some theoretical frameworks. While we observe these constants, things like the speed of light, the charge of an electron, or the strength of gravity, to be unchanging in our local environment, some theories suggest that they might evolve slowly as the universe expands and cools, changing so gradually that the effects will be noticeable only over billions of years of cosmic time. As you contemplate this cosmic cooling, you might wonder about its ultimate destination. If current models of cosmic evolution are correct, the universe will continue cooling indefinitely as expansion continues, eventually reaching temperatures so low that all molecular motion ceases and even atomic nuclei become unstable. This heat death scenario represents the ultimate endpoint of the cooling whisper, a universe expanded to such enormous size and cooled to such low temperatures that no further work can be done and no further complexity can emerge. Yet even this seemingly final state may not represent the end of cosmic evolution. Quantum mechanics suggests that even in the deepest cold of expanded space, virtual particles will continue to appear and disappear, and over unimaginably long time periods. Random quantum fluctuations might recreate conditions similar to those that gave birth to our current universe. The cooling whisper that seems to lead toward heat death might actually be preparing the stage for new forms of cosmic breathing that operate on timescales so vast they make the current age of the universe seem like a brief moment. The beauty of the cosmic cooling lies partly in its universality and inevitability. Unlike local temperature changes that can be reversed by adding energy or changing conditions, the cosmic cooling represents a fundamental trend that affects every corner of the universe simultaneously. Yet this cooling is not a loss or a failure, but rather an enabling process that has made possible every complex structure and every moment of beauty in cosmic history. As you rest now in awareness of this gentle cooling that surrounds and includes you, consider how the very atoms in your body have been participants in this cosmic temperature drop for billions of years. The carbon in your cells, the oxygen you breathe, the iron in your blood, all of these elements were forged in the hot cores of ancient stars and have since been cooled by billions of years of cosmic expansion. Your body temperature of 98.6 degrees Fahrenheit represents a tiny island of warmth in a universe that is cooled to an average temperature just a few degrees above absolute zero. The cooling whisper of cosmic expansion continues even now, as gentle and inevitable as the gradual settling of evening shadows across a peaceful landscape. In this cosmic cooling, we find not the end of possibilities, but the continuous creation of new conditions for existence, new opportunities for complexity and beauty to emerge from the evolving patterns of an expanding, breathing, slowly cooling universe. As you settle deeper into contemplation of the cosmic breath, feeling perhaps the gentle rhythm of your own breathing synchronizing with these vast universal patterns, you begin to sense one of the most poetic and profound aspects of cosmic expansion, the way that entire galaxies, those magnificent island universes containing hundreds of billions of stars, slowly and gracefully drift apart from one another like dancers in a cosmic ballet that unfolds across billions of years. This galactic separation represents perhaps the most visible and emotionally resonant manifestation of the universe's great exhale, a process so gentle that it can barely be measured over human lifetimes, yet so inexorable that it will ultimately reshape the cosmic landscape beyond recognition. To truly appreciate this galactic drift, imagine that you could observe the universe from a vantage point far above the local group of galaxies that includes our own Milky Way, with the ability to watch time unfold at an accelerated pace where millions of years pass like minutes. From this cosmic perspective, you would witness a scene of extraordinary beauty and melancholy, vast spiral and elliptical galaxies slowly rotating in their eternal dance while simultaneously growing more distant from their neighbors, like luminous flowers in a garden where the space between each bloom gradually increases with the passage of time. Our own Milky Way galaxy participates in this cosmic drift, though its motion is complex and nuanced, influenced by the gravitational relationships within our local galactic neighborhood. The nearest large galaxy to our own is Andromeda, a magnificent spiral galaxy located approximately 2.5 million light-years away and approaching us at a speed of about 110 kilometers per second. This approach might seem to contradict the general pattern of cosmic expansion, but it actually represents a local gravitational interaction that will play out over the next several billion years before the larger pattern of expansion ultimately takes control. The gravitational dance between the Milky Way and Andromeda represents one of the last intimate encounters that will occur in our local cosmic neighborhood. In approximately 4.5 billion years, these two great galaxies will merge in a cosmic collision so gentle that it might be better described as an embrace. Despite containing hundreds of billions of stars each, the vast spaces between individual stars mean that this galactic merger will likely proceed without any direct stellar collisions, instead creating a new, larger elliptical galaxy that astronomers have playfully named Milkomeda. But even this future galactic merger cannot escape the influence of cosmic expansion. After the Milky Way and Andromeda complete their gravitational dance and settle into their new combined form, The resulting galaxy will find itself increasingly isolated as cosmic expansion carries all other galaxies beyond the reach of gravitational interaction. The other major galaxy in our local group, the smaller Triangulum galaxy, may also participate in this merger, but beyond our immediate galactic family, all other galaxies will slowly recede into cosmic distance. The rate at which galaxies drift apart depends on their initial separation, following the relationship discovered by Edwin Hubble in the 1920s. Galaxies that are twice as far away recede twice as fast. Galaxies that are 10 times as far away recede 10 times as fast, and so on. This relationship means that while nearby galaxies like Andromeda can still approach us due to local gravitational effects, more distant galaxies are carried away by expansion at speeds that increase with distance until they eventually exceed the speed of light itself. This superluminal recession might seem to violate Einstein's special theory of relativity, which states that nothing can travel faster than light through space. However, the galaxies themselves are not moving through space faster than light. Instead, space itself is expanding so rapidly at great distances that the cumulative effect of expansion across billions of light-years of distance creates recession speeds that exceed the speed of light. This distinction is crucial to understanding how cosmic expansion works. Galaxies are not racing through space, but are being carried along by the expansion of space itself. As galaxies drift apart, the cosmic web, that vast network of dark matter filaments that connects galaxy clusters across the universe, also stretches and evolves. Or once relatively short bridges of dark matter linking nearby galaxy clusters become increasingly elongated until they eventually snap, leaving galaxy clusters as isolated islands in an ever-expanding cosmic ocean. This evolution of cosmic structure represents one of the most significant long-term consequences of the universe's continued breathing, gradually transforming a connected cosmic web into isolated cosmic archipelagos. The stretching of space between galaxies also affects the intergalactic medium, the thin gas that fills the apparent emptiness between galaxies. As this medium expands along with space itself, it becomes increasingly tenuous, dropping below the density threshold needed for new star formation. This cosmic dilution represents one of the ways that expansion influences the future evolution of galaxies, gradually cutting off the supply of fresh gas that galaxies need to continue forming new stars. Within galaxy clusters, those massive collections of hundreds or thousands of galaxies bound together by gravity, the expansion of space creates interesting dynamics. While the cluster as a whole maintains its gravitational integrity, the spaces between individual galaxies within the cluster slowly increase. Over billions of years, galaxy clusters become less dense as their constituent galaxies drift farther apart, though they remain gravitationally bound unless the acceleration of cosmic expansion eventually overcomes even these strong gravitational ties. The observational consequences of galactic drift create some of the most profound implications for the future of astronomy and cosmology. As galaxies recede from us due to expansion, their light becomes increasingly redshifted, making them appear fainter and redder over time. Galaxies that are currently at the edge of our observational capability will eventually fade beyond detectability as their light is redshifted into wavelengths we cannot observe and their apparent brightness drops below the sensitivity limits of even our most powerful telescopes. This cosmic fading means that future observers, living billions of years from now in the Milkomeda galaxy, will inhabit a universe that appears fundamentally different from the one we observe today. The cosmic microwave background radiation will have been redshifted and cooled to such an extent that it may no longer be detectable. The light from distant galaxies will have faded beyond observation. Future astronomers may find themselves in a universe that appears to contain only their own galaxy, surrounded by apparently empty space stretching to infinity. This scenario, sometimes called the Big Rip or cosmic horizon, represents one of the most poignant aspects of cosmic expansion. The very process that enabled the formation of galaxies and made possible the emergence of stars, planets, and life will eventually hide most of the universe from view, creating cosmic loneliness on scales that challenge human comprehension. Yet, even in this apparent isolation, the fundamental processes of stellar evolution, planetary formation, and potentially biological evolution could continue within individual galaxies for trillions of years. The drift of galaxies also affects the cosmic perspective available to any potential civilizations that might exist now or in the future. We are fortunate to live during a cosmic epoch when a universe is old enough for complex structures to have formed, yet young enough that much of cosmic history remains visible to our observations. We can see galaxies in various stages of evolution, from young, star-forming spirals to ancient, evolved ellipticals, providing us with a cosmic laboratory for understanding galactic evolution. Future civilizations, living in an era when cosmic expansion has carried most galaxies beyond the observable horizon, will have access to a much more limited cosmic perspective. They may need to rely on archaeological astronomy, studying the relics and remnants left behind by cosmic evolution to piece together the history of the universe that we can observe directly today. The timescales over which galactic drift occurs are almost incomprehensibly vast from human perspective. The changes in galactic positions that result from cosmic expansion are so gradual that they cannot be detected over human lifetimes or even over the entire history of human civilization. Only through careful measurements of very distant galaxies, whose light has been traveling toward us for billions of years, can we observe the effects of this cosmic breathing directly. Yet despite these vast timescales, the process of galactic drift connects intimately with human existence and perspective. The atoms in your body were forged in stars within galaxies that have been participating in cosmic expansion for billions of years. The light reaching your eyes from distant galaxies has been stretched and reddened by billions of years of cosmic breathing. Your consciousness, contemplating these cosmic processes, represents a temporary local concentration of matter and energy that emerged within the expanding universe and will eventually return to it. As you rest now in awareness of this galactic drift, feeling perhaps the way these cosmic movements mirror the gentle, rhythmic flows of your own body, the circulation of blood, the rhythm of breathing, the slow pulse of neural activity, you can sense yourself as a participant in patterns that operate on every scale from the subatomic to the cosmic. The same fundamental forces and processes that carry galaxies apart across billions of light years also maintain the delicate balances within your own body that make consciousness and contemplation possible. The galaxies drift apart with the patience of eternity, following trajectories determined by the interplay of cosmic expansion and gravitational attraction, creating a universe that grows ever larger and more sparse while maintaining the essential conditions for complexity, beauty, and wonder to continue emerging within the islands of matter that remain bound together by gravity and proximity in the vast, breathing cosmos. As you continue to follow the gentle rhythm of the universe's breathing, feeling perhaps the way your own breath naturally settles into deeper, more peaceful patterns, you begin to sense something profound about the nature of cosmic rhythms. The possibility that even the vast exhalation we have been exploring might eventually reach a moment of pause, a cosmic instant of perfect equilibrium where the outward breath of expansion comes to rest before potentially beginning an equally majestic inhalation. This cosmic pause represents one of the most intriguing and peaceful concepts in cosmology, a theoretical moment when a universe might achieve perfect balance between the forces that drive expansion and those that resist it. To understand this cosmic pause, imagine yourself floating in the perfect stillness that exists between breaths. That serene moment when your lungs have finished exhaling but have not yet begun to inhale, when your body exists in perfect equilibrium with the surrounding air, when all the processes of respiration pause in harmonious balance. Now expand this concept to encompass the entire universe, envisioning a cosmic moment when space itself might pause between expansion and contraction, when the outward flow of the great exhale reaches its maximum extent and comes to rest in perfect cosmic stillness. The possibility of such a cosmic pause emerges from our understanding of the competing forces that govern the universe's evolution. On one side stands a momentum of expansion, driven by the initial energy of the Big Bang and currently accelerated by the mysterious dark energy that permeates space. On the other side lies the gravitational attraction of all the matter in the universe, constantly working to slow the expansion and potentially reverse it. The cosmic pause would represent the theoretical moment when these opposing forces achieve perfect balance, when expansion neither accelerates nor decelerates, but simply comes to rest. In current cosmological models, this cosmic pause seems unlikely to occur in our universe's future, since observations suggest that dark energy will continue to accelerate expansion indefinitely. However, the concept remains valuable as a thought experiment that helps us understand the delicate balance of forces that governs cosmic evolution, and it opens the door to contemplating alternative scenarios where the universe's breathing might follow different patterns than those we currently observe. If such a cosmic pause were to occur, it would represent a moment of extraordinary cosmic significance, a time when the entire universe would exist in perfect equilibrium, neither expanding nor contracting, neither heating nor cooling through adiabatic processes, but simply being in a state of cosmic rest. During this pause, space itself would neither grow larger nor smaller, maintaining constant distances between all unbound objects throughout the cosmos. The duration of this hypothetical cosmic pause would depend on the precise balance of forces involved. In some theoretical scenarios, the pause might last only an instant, a single moment of perfect balance before gravitational forces begin to dominate and initiate cosmic contraction. In others, the pause might extend for billions or even trillions of years, creating a cosmic epoch characterized by stability and equilibrium rather than the dynamic change that has characterized the universe's history so far. During an extended cosmic pause, the universe would enter a phase unlike any it has experienced since the very early moments after the Big Bang. Without the ongoing expansion to drive adiabatic cooling, the temperature of intergalactic space would stabilize at whatever value it had reached at the moment of pause. The cosmic microwave background radiation would no longer continue its redshift toward longer wavelengths, but would maintain a constant temperature and frequency throughout space. Galaxies during the cosmic pause would find themselves in a unique gravitational environment. Without cosmic expansion to carry them apart, galaxies that are currently receding from each other would instead be governed purely by their mutual gravitational attractions. Over the billions of years of a cosmic pause, this could lead to significant changes in the large-scale structure of the universe, as gravity gradually reshapes the cosmic web without the competing influence of expansion. The pause would also affect the evolution of individual galaxies in profound ways. Currently, cosmic expansion gradually cuts off the supply of fresh intergalactic gas that galaxies need for continued star formation. During a cosmic pause, this gas would no longer be diluted by expansion, potentially providing galaxies with continued access to the raw materials for new stellar birth over much longer timescales than current models predict. Dark matter, that mysterious component that makes up most of the universe's mass, would also behave differently during a cosmic pause. Without expansion to stretch the cosmic web of dark matter filaments, these structures will be governed purely by gravitational evolution, potentially leading to increased clustering and the formation of new large-scale structures that cannot develop in our current expanding universe. The quantum vacuum, the sea of virtual particles that fills apparently empty space, might also respond differently during a cosmic pause. Without the expansion of space to affect vacuum energy density, quantum fluctuations might evolve according to different patterns, potentially affecting the fundamental properties of space itself in ways that are currently beyond our theoretical understanding. From a perspective of any hypothetical observers during a cosmic pause, the universe would present a very different appearance than the one we observe today. The cosmic redshift that currently allows us to measure distances to remote galaxies would no longer increase with time. Instead, The spectral lines of distant galaxies would maintain constant wavelengths, creating a static cosmic distance scale that would remain unchanged across billions of years. The cosmic microwave background, instead of continuing its gradual cooling and redshift, would maintain constant properties throughout the pause. This could provide future observers with a remarkably stable cosmic reference frame, a universal background against which to measure local changes in evolution without the complicating effects of ongoing cosmic expansion. Perhaps most intriguingly, a cosmic pause might represent an opportunity for consciousness and intelligence to achieve new forms of cosmic perspective. Without the time pressure created by ongoing expansion and the eventual heat death it implies, civilizations during the pause might have effectively unlimited time to explore the cosmos, to understand the deepest principles of physics, and to develop forms of existence and awareness that are impossible within the time constraints of our current expanding universe. The transition into a cosmic pause, if it were to occur, would be so gradual as to be imperceptible to any observers living through it. The deceleration of cosmic expansion would occur over billions of years, with each generation of observers finding the universe essentially unchanged from their predecessors' observations. Only by maintaining careful measurements across cosmic time would it become apparent that the universe was approaching this moment of perfect balance. Similarly, the transition out of a cosmic pause, whether toward renewed expansion or the beginning of cosmic contraction, would occur with the same sublime gradualism. The first signs might be detected only through the most sensitive measurements of cosmic distances and recession velocities, as the universe begins to tip from perfect equilibrium toward whatever cosmic phase would follow the pause. The mathematics describing a cosmic pause involve some of the most elegant equations in cosmology, representing the precise balance between kinetic energy of expansion and potential energy of gravitational attraction. At the moment of cosmic pause, these energies would be perfectly equal, creating a state that physicists describe as having zero total energy, a condition that some theories suggest might be fundamental to the universe's existence. Theoretical physicists have explored variations on the cosmic pause concept, including scenarios where different regions of the universe might pause at different times, creating a patchwork cosmos where some areas continue expanding while others enter periods of equilibrium. These models suggest that cosmic breathing might be more complex than a simple universal rhythm, with different cosmic regions following their own individual breathing patterns. The concept of cosmic pause also connects to deeper questions about the nature of time itself. During a period when space neither expands nor contracts, when cosmic evolution enters a stable equilibrium, the relationship between cosmic time and local time might take on new characteristics. Time would continue to flow for local observers, but cosmic time, the universal clock that has been marked by expansion since the Big Bang, might enter a period of suspended animation. As you contemplate this possibility of cosmic pause, resting in the quiet space between your own breaths, you can sense how this theoretical moment represents not an ending, but a potential point of perfect balance. A cosmic meditation where the universe achieves a state of profound rest before potentially beginning new phases of its evolution. Whether or not such a pause will ever occur in our universe's future, the concept reminds us that cosmic breathing, like all natural rhythms, contains moments of rest as well as motion, periods of stillness as well as change. In this cosmic pause, we find a mirror for the peaceful moments in our own experience, those instants of perfect balance when we pause between activity and rest, between thought and contemplation, between the inhalation and exhalation of our own breathing. The universe, in all its vast complexity, might someday achieve its own version of this peaceful pause, resting in perfect equilibrium while maintaining all the conditions necessary for consciousness, beauty, and wonder to continue their own evolutionary journeys through cosmic time. As you rest in the peaceful stillness that follows our contemplation of cosmic pause, feeling perhaps the natural rhythm of your own breathing as it prepares to draw air gently back into your lungs, you begin to sense the possibility of an equally beautiful and profound phase in the universe's breathing. The potential for a gentle cosmic inhale that might follow the pause, a gradual reversal of expansion that would slowly, peacefully, and majestically draw all of space back together in a process as natural and inevitable as the breath returning to your body after a moment of perfect stillness. This cosmic inhale, should it ever occur, would represent one of the most remarkable phenomena imaginable. The entire universe beginning to contract, with space itself slowly growing smaller, carrying galaxies gently back toward each other like dancers in a cosmic ballet performed in reverse. Unlike the violent collapse that might spring to mind when we first consider cosmic contraction, this process would unfold with the same sublime gradualism that has characterized cosmic expansion, taking billions upon billions of years to transform the expanding cosmos into a contracting one. To understand the nature of this gentle inhale, imagine watching a film of cosmic expansion played in reverse at an incredibly slow speed. Galaxies that have been drifting apart for billions of years would gradually slow their recession, come to rest, and then begin a stately approach toward each other. The cosmic microwave background radiation, instead of continuing to redshift toward longer wavelengths, would begin to blue shift back toward shorter, more energetic frequencies. Space itself would begin the long process of growing smaller, carrying with it all the matter, energy, and structure that expansion had spread across cosmic distances. The mechanism that could drive such a cosmic inhale would necessarily involve a fundamental change in the balance of forces governing cosmic evolution. Currently, dark energy drives accelerating expansion, overpowering the gravitational attraction of matter. For contraction to begin, either dark energy would need to weaken or reverse its effect, or gravitational forces would need to strengthen relative to the expansion drive. Some theoretical models suggest that dark energy might not remain constant over cosmic time, potentially evolving in ways that could eventually favor contraction over expansion. Alternative theories propose that our current phase of accelerating expansion might be temporary, representing just one cycle in an eternal series of cosmic breathing cycles. In these oscillating universe models, expansion and contraction alternate over timescales so vast that the current age of the universe represents merely a brief moment in the cosmic exhale phase of one such cycle. The gentle inhale would then be as natural and inevitable as the exhale, part of an eternal cosmic rhythm that has been repeating for infinite time. As the cosmic inhale proceeds, the first observable effects would be incredibly subtle, detectable only through the most precise measurements of cosmic distances and galaxy velocities. Galaxies that were once receding from us would gradually slow their recession until they came to rest relative to our cosmic reference frame. Then, almost imperceptibly, they would begin to approach, initially at speeds so slow that thousands of years might pass before the change became clearly apparent. The reversal of cosmic expansion would affect the cosmic microwave background in beautiful and fundamental ways. This primordial radiation, which has been cooling and redshifting for nearly 14 billion years, would begin to warm and blue shift as space contracted around it. Instead of the gentle, cooling whisper we explored earlier, the cosmos would begin to experience a gradual warming that might eventually restore the microwave background to visible light frequencies, recreating conditions reminiscent of the universe's younger days. Dark matter, that invisible scaffolding that gives structure to the cosmos, would respond to contraction by becoming increasingly dense and concentrated. The cosmic web of dark matter filaments that currently spans billions of light years would slowly contract, bringing galaxy clusters closer together and potentially enabling new forms of gravitational interaction between cosmic structures that are currently too distant to influence each other significantly. Galaxies themselves would experience the cosmic inhale as a gradual change in their cosmic environment. Instead of the slow starvation of star formation caused by expanding space diluting the intergalactic medium, Contracting space would concentrate this medium, potentially providing galaxies with renewed access to fresh gas for star formation. This could initiate a cosmic renaissance of stellar birth, with galaxies experiencing increased star formation rates as the universe contracts around them. The process of cosmic contraction would also reverse many of the effects of expansion on light traveling through space. Photons that have been stretched to longer wavelengths by billions of years of expansion would find themselves compressed back to shorter wavelengths as they continue their journey through contracting space. Light from distant galaxies, instead of appearing redshifted, would begin to appear blue-shifted, with the amount of blue shift increasing from more distant sources. This reversal of cosmic redshift would transform astronomical observation in profound ways. Distant galaxies that currently appear red and faint due to expansion-induced redshift would gradually become bluer and brighter as contraction-induced blue shift took effect. The most distant galaxies, which currently require our most powerful telescopes to detect, might eventually become visible to the naked eye as their light becomes concentrated and blue-shifted by cosmic contraction. The timeline of cosmic inhale would mirror the expansion timeline in reverse, but with its own unique characteristics determined by the specific mechanism driving contraction. If contraction were driven by a reversal of dark energy, the initial phases might proceed slowly, gradually accelerating as the anti-expansion force grew stronger. If driven by gravitational collapse, overcoming expansion, the process might begin slowly, but then accelerate dramatically as matter density increased with contraction. During the early phases of cosmic inhale, when contraction rates remained relatively modest, the universe would still provide a hospitable environment for the continuation and evolution of complex structures. Stars would continue to shine, planets would continue to orbit, and life, if it exists elsewhere in the cosmos, could continue to evolve and develop consciousness capable of observing and appreciating the cosmic breathing cycle they were experiencing. The intermediate phases of cosmic contraction would bring galaxy clusters back into close proximity, reversing billions of years of cosmic expansion and recreation, the connected cosmic web that characterized the universe's youth. Galaxies that had been isolated by expansion would find themselves once again embedded in rich cosmic environments, with renewed opportunities for gravitational interaction, gas exchange, and a large-scale structure formation that expansion had prevented. As cosmic contraction progressed, the increasing density of matter and energy would begin to affect the fundamental physics operating throughout the universe. The strength of gravitational fields would increase as matter concentrated into smaller volumes. The frequency and intensity of matter interactions would increase as particles and structures were brought closer together. The universe would begin to experience a gradual reversal of the cooling and rarefaction that had characterized the expansion phase. The quantum vacuum would also respond to cosmic contraction in ways that might reveal new aspects of fundamental physics. As space contracted, virtual particle pairs that constantly appear and disappear in empty space might experience different energy densities and interaction rates. These changes could potentially affect the fundamental constants of nature or reveal new physical phenomena that operate only during cosmic contraction phases. Perhaps most remarkably, cosmic contraction would offer conscious observers the opportunity to witness cosmic evolution proceeding in reverse, to see the universe retracing its evolutionary steps and potentially revealing new insights about the fundamental nature of time, causality, and cosmic structure. Civilizations living through a cosmic inhale would have the unique privilege of observing cosmic history playing backward, seeing how structures that formed during expansion would behave as space carried them back together. The reversal of cosmic expansion would also affect the relationship between local time and cosmic time in fascinating ways. While local clocks would continue to tick forward normally, the cosmic clock that has been advancing through expansion since the Big Bang would begin to run backward. This might create interesting philosophical questions about the nature of time and whether cosmic contraction represents a movement toward the past or simply a different direction of temporal flow. The temperature evolution during cosmic inhale would reverse the cooling trend that has characterized cosmic expansion, gradually warming the universe as matter and energy became concentrated into smaller volumes. This warming would proceed slowly at first, but could eventually reach temperatures that significantly affect the evolution of matter and energy throughout the cosmos. As you contemplate this possibility of cosmic inhale, feeling perhaps the way your own breath naturally draws air back into your lungs after the pause between breaths, you can sense how this process would represent not a reversal or undoing of cosmic evolution, but rather a new phase in the universe's development. Just as your inhale doesn't negate your exhale, but rather continues the cycle of breathing that sustains your life. A cosmic inhale would continue the cycle of cosmic breathing that might sustain the universe's existence across infinite cycles of expansion and contraction. The gentle cosmic inhale reminds us that even on the vastest scales, the patterns that govern existence might follow rhythms as natural and peaceful as our own breathing. Cycles of expansion and contraction, separation and reunion, exhale and inhale that continue the eternal dance of cosmic existence through transformations that encompass all of space and time while maintaining the essential conditions for beauty, complexity, and consciousness to flourish within the breathing universe. As you settle deeper into the rhythm of cosmic breathing, feeling perhaps the way your own breath naturally draws life-giving air back into your body, gathering oxygen from the atmosphere and bringing it home to nourish every cell in your being, you begin to understand one of the most beautiful and profound aspects of cosmic contraction. The way this gentle inhale would gradually draw everything in the universe back toward unity, creating a cosmic homecoming that spans billions of years and encompasses every particle, every wave of light, every structure that expansion had carried apart over the vast reaches of space and time. This cosmic drawing home would represent far more than simple reversal of expansion. It would be an active gathering process that brings together matter, energy, and information that have been separated by billions of years of cosmic breathing. Like a vast, gentle embrace that slowly encompasses everything in existence. Cosmic contraction would reunite elements of the universe that expansion had carried beyond each other's influence, creating new opportunities for interaction, connection, and the emergence of forms of complexity impossible during the expansion phase. To appreciate the profound nature of this cosmic gathering, imagine the universe as a vast family that has been scattered across immense distances by the winds of expansion, with each galaxy representing a member of this cosmic family carried far from home by circumstances beyond their control. The cosmic inhale would be the long journey home, a gradual reunion that brings these separated family members back together, allowing them to share their stories, exchange their treasures, and create new forms of connection enriched by their long separation. The process would begin subtly, with the most distant galaxies, those at the very edge of our observable universe, gradually slowing their recession and beginning their long journey back toward the cosmic center. These edge galaxies, currently receding at speeds approaching the speed of light, would find their recession gradually decreasing as cosmic contraction overcame expansion. Over billions of years, they would slow to a stop and then begin the long approach back toward the dense regions of space they left behind during expansion. As cosmic contraction progressed, it would reverse the cosmic redshift that has been stretching light for billions of years, gradually blue-shifting all electromagnetic radiation traveling through space. This would have extraordinary effects on our ability to observe and understand distant regions of the universe. Galaxies that are currently invisible to us because their light has been redshifted beyond our detection capability would gradually become visible again as contraction blue-shifted their radiation back into observable wavelengths. The cosmic microwave background radiation would experience particularly dramatic transformation during this drawing home process. This ancient light, which has been cooling and redshifting since the universe became transparent 380,000 years after the Big Bang, would begin to warm and blue shift back toward higher energies. Over the billions of years of cosmic contraction, this background radiation could potentially return to visible light frequencies, filling space with a gentle glow that would gradually brighten as contraction continued. Dark matter, that invisible scaffolding that provides the gravitational framework for cosmic structure, would play a crucial role in drawing everything home. As space contracted, the cosmic web of dark matter filaments would concentrate and strengthen, creating increasingly powerful gravitational channels that would guide the reunion of ordinary matter. Galaxy clusters that had been isolated by expansion would find themselves connected once again by dense bridges of dark matter, facilitating the exchange of gas, stars, and perhaps even biological material across cosmic distances. The reunion of galaxies would occur in stages, with the closest galaxies coming together first, followed by progressively more distant ones as contraction continued. Our own local group of galaxies, including the Milky Way, Andromeda, and their smaller companions, would be among the first to experience significant changes as galaxies that had been slowly separating due to expansion began to approach each other more rapidly under the influence of both gravity and cosmic contraction. This galactic reunion would create opportunities for cosmic-scale interactions that have been impossible during the expansion era. Galaxies that had been evolving in isolation for billions of years would begin to influence each other gravitationally, triggering new episodes of star formation, facilitating the exchange of gas and dust, and potentially creating entirely new types of galactic structures that can only form when multiple galaxies interact over extended periods. The drawing home process would also affect individual stars and planetary systems in subtle but important ways. As the density of matter in the universe increased due to contraction, the gravitational environment in which stars and planets exist would gradually intensify. This could affect the stability of planetary orbits, the behavior of stellar evolution, and the dynamics of star formation within galaxies as the cosmic environment became increasingly dense and interconnected. Stellar light traveling through contracting space would experience systematic blue shifting that would affect how energy propagates through the universe. Stars that currently appear red and cool due to cosmological redshift would gradually appear bluer and hotter as contraction reversed the expansion-induced redshift of their light. This could have significant implications for the energy balance of planetary systems, as the apparent temperature and luminosity of distant stars would increase due to contraction effects. The concentration of the intergalactic medium, the thin gas that fills the apparent emptiness between galaxies, would create new opportunities for cosmic-scale processes. Currently, this medium is so diffuse that it cannot support large-scale star formation or complex chemistry. As contraction concentrated this gas, it might become dense enough to collapse under its own gravity, potentially forming entirely new generations of stars and galaxies in regions of space that have been effectively empty during the expansion era. Perhaps most remarkably, the drawing home process would create opportunities for information and complexity that have been separated by expansion to reconnect and interact in new ways. Light signals, gravitational waves, and other forms of information that expansion had scattered across vast distances would find themselves concentrated and intensified by contraction, potentially enabling new forms of cosmic communication and interaction. The timescales of this cosmic homecoming would be vast beyond human comprehension, with different phases of the reunion occurring over different cosmic epochs. The initial slowdown and reversal of recession would take billions of years to become clearly apparent. The actual convergence of distant galaxies would require additional billions of years, while the final stages of cosmic contraction might unfold over timescales that dwarf the current age of the universe. During the intermediate phases of drawing everything home, when cosmic contraction had progressed significantly but had not yet reached extreme densities, the universe might experience a kind of cosmic renaissance. The reunion of matter and energy that had been separated by expansion could trigger new episodes of structure formation, star birth, and potentially even the emergence of new forms of life and consciousness adapted to the changing cosmic environment. The gravitational effects of drawing everything home would create fascinating dynamics on all scales. Local gravitational systems like solar systems and stellar clusters would remain stable, held together by forces much stronger than cosmic contraction. But the large-scale gravitational landscape would transform dramatically as matter concentrated and the average density of a universe increased. Galaxy clusters would merge and coalesce as contraction brought them back together, creating superclusters of unprecedented size and complexity. These merged structures would provide new laboratories for cosmic evolution, with environments that had never existed during the expansion era. The increased gravitational interactions could trigger new forms of galactic evolution, star formation, and potentially even new mechanisms for the development of complexity and organization. The cosmic web itself would transform as contraction proceeded, evolving from the stretched, attenuated structure we observe today into an increasingly dense and interconnected network. Filaments that currently span hundreds of millions of light years would contract to much smaller scales while maintaining their essential connectivity, creating a cosmic nervous system that could potentially facilitate rapid communication and interaction across the converging universe. As the drawing home process advanced, the fundamental physics operating throughout the universe would gradually shift toward the high-density, high-temperature regimes that characterize the early universe. This could reveal new physical phenomena and force laws that operate only under extreme cosmic conditions, providing insights into the fundamental nature of matter, energy, space, and time. The quantum vacuum would respond to increasing matter density and cosmic contraction in ways that might reveal new aspects of quantum field theory and the relationship between space, time, and matter. Virtual particle production rates might increase. Vacuum energy density could change, and new quantum phenomena might emerge as the universe transitioned from the low-density expansion regime to the high-density contraction regime. For any conscious observers living through this cosmic homecoming, the experience would be simultaneously humbling and awe-inspiring. They would witness the universe reversing billions of years of expansion, drawing together matter and energy that had been separated since shortly after the Big Bang. They would see distant galaxies returning like old friends coming home after a long journey, carrying with them the accumulated wisdom and complexity of billions of years of separate evolution. The emotional and philosophical implications of drawing everything home touch on some of the deepest questions about cosmic purpose and meaning. The idea that the universe might periodically gather all of its scattered elements back together suggests a cosmic pattern of separation and reunion that mirrors cycles found throughout nature. From the daily rhythm of breathing to the seasonal cycles of plant growth and dormancy to the longer cycles of stellar and galactic evolution. As you rest now in contemplation of this cosmic homecoming, feeling perhaps the way your own breath draws the atmosphere back into your body, gathering oxygen from the vast sky and bringing it home to nourish your being, you can sense how this cosmic process reflects universal patterns of gathering and sharing, separation and reunion that operate on every scale from the molecular to the cosmic, creating an endless dance of connection that ensures nothing is ever truly lost. Everything eventually finds its way home, and the universe maintains its essential unity even as it breathes through cycles of expansion and contraction across the infinite reaches of space and time. As the cosmic inhale continues its gentle work of drawing everything home, something beautiful and fundamental begins to happen throughout the contracting universe. A gradual warming that spreads through every corner of space like the slow kindling of a cosmic fire. Or perhaps more accurately, like the gentle warming that occurs when you draw breath into your lungs, bringing the ambient temperature of air into intimate contact with the warmth of your body. This cosmic warming represents the reverse of the cooling whisper we explored during expansion, a process that slowly and peacefully restores energy and heat to a universe that had been cooling for billions of years. To understand this warm embrace of cosmic contraction, imagine the universe as a vast chamber that has been slowly cooling for nearly 14 billion years as its volume expanded and its energy became diluted across ever larger regions of space. Now, as contraction begins, this cosmic chamber starts to compress, gently squeezing all the matter and energy it contains into smaller and smaller volumes, causing temperatures to rise through the same fundamental physical processes that make air warm when it's compressed, but occurring so gradually and gently that the warming unfolds over billions of years with the patience of geological time. This cosmic warming begins subtly, with the first detectable effects appearing in the cosmic microwave background radiation, that ancient afterglow of the Big Bang that has been cooling and redshifting throughout the expansion era. As space begins to contract, this background radiation experiences the reverse of the redshift that has been stretching its wavelengths toward longer, cooler frequencies. Instead, it begins to blue shift back toward shorter, more energetic wavelengths, gradually warming from its current temperature of 2.7 degrees above absolute zero toward higher and higher temperatures. The rate of this warming follows the inverse of the cooling process that occurred during expansion, where expansion caused adiabatic cooling as energy spread over larger volumes. Contraction causes adiabatic heating as energy becomes concentrated into smaller spaces. This heating is not violent or sudden, but rather represents a gradual restoration of the energy density that expansion had diluted, like slowly turning up a cosmic thermostat that had been gradually cooling the universe for billions of years. As the cosmic microwave background warms, it begins to affect the evolution of matter throughout the universe in subtle but increasingly important ways. Currently, this background radiation is so cool that it has negligible effects on the behavior of stars, planets, and other cosmic structures. But as contraction warms it to higher temperatures, it begins to provide a significant energy input to cosmic processes, potentially affecting everything from the formation of stars to the evolution of planetary atmospheres. The warming process affects different types of matter and energy in different ways, creating a complex symphony of thermal evolution throughout the contracting universe. Gas clouds that have been cooled to near absolute zero by billions of years of expansion begin to warm as they're compressed by cosmic contraction. This warming can trigger new episodes of star formation as gas clouds that were too cold to collapse under their own gravity gain enough thermal energy to begin the complex processes that lead to stellar birth. Dark matter, that mysterious component that makes up most of the universe's mass, also participates in the cosmic warming in ways that are still not fully understood by theoretical physics. While dark matter doesn't interact electromagnetically and therefore doesn't directly absorb or emit heat in the way ordinary matter does, it does respond to gravitational compression. As space contracts and dark matter becomes denser, the gravitational interactions within dark matter structures intensify, potentially leading to new forms of dark matter behavior that could affect the warming process. The warming embrace extends beyond just temperature changes to encompass a general increase in energy density throughout the universe. As space contracts, not only does matter become more concentrated, but all forms of energy, electromagnetic radiation, gravitational fields, and even the mysterious dark energy that currently drives expansion become compressed into smaller volumes. This energy concentration creates new opportunities for interactions and processes that were impossible in the cooler, more dilute environment of the expanding universe. Stars throughout the contracting universe would experience this warming as a gradual change in their cosmic environment. The increased background temperature would affect stellar evolution by altering the rate at which stars can radiate energy into space. Stars that currently lose heat efficiently to the cold cosmic background would find this cooling process gradually becoming less effective as the background temperature rises, potentially extending stellar lifetimes and changing the patterns of stellar evolution. Planetary systems would experience the cosmic warming as a slow but significant change in their energy balance. Planets that currently receive most of their energy from their host stars would gradually begin to receive additional energy from the warming cosmic background. This additional energy input could have profound effects on planetary atmospheres, weather patterns, and potentially even the habitability of worlds throughout the universe. The warming process would also affect the behavior of light and other electromagnetic radiation traveling through space. As space contracts and its energy density increases, photons traveling through this warming medium experience systematic blue shifting that not only changes their wavelength, but also increases their energy. Light from distant stars and galaxies would arrive at Earth not only bluer than when it was emitted, but also carrying more energy per photon due to the compression effects of cosmic contraction. Perhaps most remarkably, the cosmic warming would begin to reverse many of the effects of the cosmic cooling that has been occurring since shortly after the Big Bang. Processes that became impossible as the universe cooled and expanded might gradually become possible again as warming and contraction restore the energy densities needed for high-energy physics and exotic matter states. The timeline of cosmic warming would follow a complex pattern determined by the interplay between contraction rate and energy density. Initially, when contraction rates are modest, warming would proceed slowly and gently. As contraction accelerated and space became smaller, warming would accelerate as well, potentially reaching rates that could significantly affect cosmic evolution within astronomically reasonable time periods. During the early phases of cosmic warming, when temperatures had risen but remained relatively modest, the universe would still provide hospitable conditions for the continuation and evolution of complex structures. The additional energy from warming might actually enhance the conditions for life and consciousness by providing more energy sources and enabling new chemical and physical processes. As warming continued through intermediate phases, reaching temperatures comparable to those in stellar cores or the early universe, more exotic physical processes would become possible. Nuclear fusion might occur spontaneously in space, creating new elements and energy sources. Particle production from vacuum energy might increase dramatically, filling space with exotic matter states that don't exist under current cosmic conditions. The warming would also affect the fundamental structure of space and time itself in ways predicted by theories of quantum gravity and cosmology. As energy densities approached those that existed in the very early universe, space-time might begin to exhibit properties that are currently hidden from observation. Extra dimensions might become apparent, fundamental constants might begin to change, and new physical laws might emerge from the high-energy cosmic environment. The quantum vacuum, which currently maintains a low energy density due to cosmic expansion and cooling, would respond dramatically to cosmic warming. Virtual particle production rates would increase exponentially as energy densities rose, potentially creating a universe filled with exotic particles and fields that exist only under extreme cosmic conditions. These quantum effects could transform the very nature of space itself, creating new phenomena that bridge the gap between quantum mechanics and cosmic scale physics. For any conscious observers experiencing cosmic warming, the process would represent one of the most profound transformations imaginable. They would witness the universe gradually returning to conditions reminiscent of its youth, watching as cosmic background temperatures rose from the frigid cold of the expansion era toward the warmth that characterized earlier cosmic epochs. They would see new physical processes emerging as energy densities increased, new forms of matter and energy appearing as the quantum vacuum responded to warming, and new opportunities for cosmic evolution opening as the universe regained access to high-energy physics. The emotional and spiritual dimensions of cosmic warming touch on themes of renewal, restoration, and return. The idea that the universe might periodically warm itself through contraction suggests a cosmic pattern of cooling and warming, rest and activity, that mirrors cycles found throughout nature. Just as winter gives way to spring, cosmic cooling might give way to cosmic warming in an eternal cycle of cosmic seasons. The warming embrace also represents a kind of cosmic intimacy, as all the matter and energy in the universe draws closer together, sharing heat and energy in ways that were impossible during the cold isolation of expansion. This cosmic coming together creates opportunities for connection, interaction, and the emergence of new forms of complexity that require the energy and proximity that only cosmic warming can provide. As temperatures rise throughout the contracting universe, chemical and physical processes that have been frozen out by billions of years of cosmic cooling gradually become possible again. Complex molecules that can only form at higher temperatures might appear spontaneously in space. New forms of plasma and exotic matter states might fill the warming cosmic medium. High-energy particle interactions that have been suppressed by low cosmic temperatures might resume, creating a renaissance of cosmic chemistry and physics. The warming process would also create new opportunities for energy transfer and communication across cosmic distances. Higher background temperatures would enable more efficient energy transmission, while increased particle densities would provide new media for information transfer. The universe would gradually transition from the cold, sparse isolation of expansion toward the warm, dense connectivity of contraction. As you contemplate this cosmic warming, feeling perhaps the way warmth spreads through your body when you breathe deeply and slowly, drawing warm air into your lungs and feeling it spread life and energy throughout your being. You can sense how this cosmic process represents not just a change in temperature, but a fundamental transformation in the nature of cosmic existence. The warm embrace of cosmic contraction would restore to the universe energies and possibilities that expansion had gradually removed, creating new chapters in cosmic evolution that would unfold in the warming, contracting, increasingly intimate environment of a universe, drawing all of its elements back together in a cosmic embrace that encompasses everything that exists across the vast scales of space and time. As you reach the peaceful culmination of our journey through cosmic breathing, feeling perhaps the way your own breath has settled into deeper, more tranquil patterns during our contemplation together, you arrive at one of the most beautiful and profound realizations about the nature of existence itself. That the cosmic breathing we have explored together might not be a single, linear process with a clear beginning and end, but rather part of an eternal rhythm that has been pulsing through reality for infinite time. A cosmic heartbeat so vast and slow that entire universes represent merely single breaths in an endless cycle of expansion and contraction, exhale and inhale, that continues forever across timescales that dwarf imagination. This eternal rhythm suggests that our universe, with all its galaxies, stars, planets, and the precious emergence of life and consciousness it has nurtured, might be just one breath in an infinite series of cosmic respirations. The Big Bang that began our current cosmic epoch might have been preceded by the big crunch of a previous universe, which was itself preceded by another expansion, which was preceded by another contraction, in an endless cycle of cosmic breathing that has no beginning and will have no end. To understand this eternal rhythm, imagine that you could somehow step outside of time itself and observe the cosmic breathing pattern from a perspective that encompasses infinite duration. From this impossible vantage point, you would see universe after universe expanding from cosmic seeds, growing through billions of years of stellar and galactic evolution, reaching maximum expansion, and then gently contracting back to singularities that become the seeds for new cosmic epochs. Each complete cosmic breath might take hundreds of billions or even trillions of years. Yet from the eternal perspective, these vast cycles would appear as natural and rhythmic as your own breathing. This cyclical vision of cosmic existence addresses some of the deepest questions that have puzzled philosophers and cosmologists for centuries. If the universe had a beginning in the Big Bang, what existed before that beginning? If cosmic expansion continues forever, leading to heat death and the end of all activity, does that represent the ultimate futility of existence? The eternal rhythm offers a different perspective, one where beginnings and endings are merely phases in ongoing cycles, where what appears to be the end of one cosmic epoch is actually the preparation for the beginning of another. In this eternal framework, the heat death that might result from indefinite cosmic expansion would not represent the final end of existence, but rather a kind of cosmic winter, a necessary period of rest and simplification that prepares the universe for its next phase of development. Just as the apparent death of plants in autumn enables the renewal of spring, cosmic heat death might enable cosmic rebirth through mechanisms we do not yet understand, but which operate according to the same principles of cyclical renewal that govern natural processes at every scale. The mechanism that could drive such eternal cosmic breathing might involve the fundamental properties of space, time, matter, and energy in ways that current physics has only begun to explore. Some theoretical models suggest that the vacuum energy of empty space might oscillate between states that favor expansion and states that favor contraction, creating cosmic cycles driven by quantum fluctuations operating on cosmic scales. Other models propose that the fundamental constants of nature might evolve cyclically, periodically changing the balance between expansion and contraction forces. Perhaps most intriguingly, some theories suggest that consciousness itself might play a role in cosmic cycles, with the emergence of awareness and intelligence in each cosmic epoch somehow influencing the transition between expansion and contraction phases. In this view, conscious observers are not merely passive witnesses to cosmic evolution, but active participants whose very existence helps shape the cosmic breathing pattern that governs universal development. The eternal rhythm also offers a perspective on the arrow of time that transcends our usual understanding of temporal flow. While we experience time as flowing from past to future in a linear progression, cosmic breathing cycles might involve more complex temporal patterns where contraction phases involve different relationships between cause and effect, past and future, than we experience during expansion phases. The universe might literally breathe time itself, expanding temporal dimensions during cosmic exhale and contracting them during cosmic inhale. Each cosmic breath in the eternal rhythm would be unique, shaped by the specific conditions and evolutionary patterns that developed during that particular cycle. While the fundamental physical laws might remain the same across cosmic epochs, the specific forms of matter, energy, and structure that emerge could vary dramatically from one cosmic breath to another. Our current universe, with its particular mix of matter and dark energy, its specific patterns of galaxy formation, and its emergence of carbon-based life, represents just one possible variation in an infinite series of cosmic experiments. The information and complexity that develop during each cosmic epoch might not be lost when that universe contracts toward its next cosmic seed. Quantum mechanical processes and gravitational memory effects might preserve essential information across cosmic cycles, allowing each new universe to begin with subtle influences from previous cosmic epochs. In this way, the eternal rhythm becomes not just repetitive cycling, but evolutionary development, with each cosmic breath building upon the achievements and discoveries of previous cycles. This information preservation across cosmic cycles offers a kind of cosmic reincarnation, where the patterns and relationships that develop during one universal epoch influence the development of subsequent universes. The carbon atoms in your body, the patterns of thought in your mind, the love and consciousness you experience, all of these might carry forward into future cosmic cycles in forms transformed but not destroyed by the cosmic breathing process. The timescales of eternal cosmic breathing challenge every human intuition about duration and permanence. A single cosmic breath might encompass trillions of years, during which countless generations of stars are born and die, countless civilizations might rise and fall, countless forms of beauty and consciousness might emerge and flourish. Yet from a perspective of eternal rhythm, these vast epochs represent merely moments in an endless cosmic meditation. For conscious beings existing within such cosmic cycles, the eternal rhythm offers both humbling perspective and profound comfort. On one hand, it suggests that even the vastest human achievements and the most enduring human institutions represent merely brief episodes in cosmic cycles so vast they approach infinity. On the other hand, it suggests that consciousness and existence are not temporary accidents in an indifferent universe, but integral aspects of cosmic processes that continue forever. The eternal rhythm also implies that the universe possesses a kind of cosmic memory that transcends any individual cosmic epoch. The patterns of cosmic breathing, the relationships between expansion and contraction, the emergence of complexity and consciousness, all of these represent cosmic learning processes that develop and refine across infinite cycles of universal development. Perhaps most beautifully, the eternal rhythm suggests that we are not isolated accidents in a hostile universe, but integral participants in cosmic processes that connect us to both the infinite past and the infinite future. Every breath you take participates in patterns that mirror cosmic breathing. Every heartbeat echoes rhythms that operate on cosmic scales. Every moment of consciousness represents the universe experiencing itself through forms that have been developing across infinite cosmic cycles. The cycles within cycles that characterize eternal cosmic breathing create a fractal pattern of rhythm and renewal that operates on every scale from the quantum to the cosmic. Just as your breathing contains smaller cycles of cellular respiration and larger cycles of daily and seasonal rhythms, cosmic breathing might contain cycles within cycles. Perhaps galactic breathing patterns within cosmic breathing patterns, stellar breathing patterns within galactic ones, atomic breathing patterns within stellar ones, creating an infinite hierarchy of rhythmic processes that connect the smallest and largest scales of existence. The meditation and peace that come from contemplating eternal cosmic breathing arise partly from recognizing our deep participation in patterns that transcend individual existence while remaining as intimate and immediate as our own breath. We are not separate from cosmic rhythms, but expressions of them, temporary patterns in eternal flows, unique moments in infinite cycles that connect us to everything that has ever existed and everything that ever will exist. The eternal rhythm reminds us that existence itself might be the point rather than any particular achievement or destination within existence. The cosmic breathing continues not to reach some final goal, but because the process of breathing, the cycles of expansion and contraction, creation and dissolution, emergence and return, is itself the fundamental expression of cosmic creativity and joy. As you rest now in awareness of these eternal rhythms, feeling perhaps the way your own breathing has synchronized with patterns that connect you to cosmic processes operating across infinite time, you can sense yourself not as a temporary visitor in an alien universe, but as an eternal participant in cosmic breathing that has no beginning and will have no end. Your consciousness, your love, your capacity for wonder and beauty, all of these represent the universe experiencing itself through forms that have been developing across countless cosmic cycles and will continue developing through countless more. The eternal rhythm continues around and through you even now, in the gentle expansion and contraction of your lungs, in the circulation of blood through your body, in the neural patterns that create your thoughts and dreams, in the gravitational dance of Earth and Moon and Sun, in the slow rotation of our galaxy, in the vast expansion of cosmic space itself. All of these rhythms are expressions of the fundamental cosmic breathing that has been pulsing through existence since before time began and will continue pulsing long after time ends. Sleep peacefully now, knowing that you are held within eternal rhythms that connect you to the infinite creativity of existence itself. Rest in the gentle cosmic breathing that surrounds and includes you, that created the conditions for your emergence and will continue creating new possibilities for consciousness and beauty across infinite cycles of cosmic development. Dream sweetly within the eternal rhythm that makes all dreams possible, and know that your participation in cosmic breathing represents both a unique moment in infinite time and a timeless expression of the eternal patterns that give meaning and wonder to existence itself. In this eternal rhythm, we find not the end of our journey, but the recognition that every ending is also a beginning. Every breath out prepares for breathing in. Every expansion enables contraction. Every separation makes reunion possible. and every moment of consciousness represents the universe celebrating its own existence through the infinite creativity of eternal cosmic breathing that continues forever, world without end, in cycles of beauty and wonder that encompass all possibilities, while remaining as gentle and natural as the breath that flows in and out of your sleeping body throughout the peaceful night.